All right, what if I told you there's a kind of secret language in math? A language that can take the most complicated, twisty functions you can think of and just break them down into a simple, endless list of additions. It sounds kind of wild, right? Well, today, we're going to decode that language, and we're going to start with the magic trick itself.
So take a look at this. This right here is the heart of the mystery. On the left, you've got these powerful functions, the ones that describe everything from waves to exponential growth. And on the right, it just looks like a simple, never-ending addition problem. But here's the mind-blowing part. These two columns aren't just similar. They are mathematically identical. Literally the exact same thing.
And that leads us to the big question for this whole explainer. How is that even possible? How can a smooth, flowing function be perfectly described by just adding up a bunch of simple little pieces forever? That's the puzzle we're going to solve together. All right, to get our heads around this mathematical magic, we have to start with the big idea behind it all. It's really all about building something super complex out of really, really simple, predictable parts. I want you to imagine trying to build a perfect sphere using only tiny, flat Lego bricks. With just a few, it's going to look pretty blocky and rough, right? But what if you had an infinite number of infinitely small bricks? Well, then you could build a surface so smooth you couldn't tell it apart from a real sphere. And that is exactly what's happening here. Each little term in our endless sum is one of those simple building blocks, and when you put them all together, they build the perfect exact curve of the function.
But, working with infinity is a bit tricky. It can be dangerous. If you add up the wrong things, your sum can just explode and shoot off to, well, infinity. So to build anything useful, our endless sum has to be controlled. It needs to settle down and land on one specific finite number. And that critical rule, that idea, is called convergence.
Okay, so it all starts with the most basic piece of the puzzle, a sequence. And really, a sequence is just a list of numbers in a particular order. That's it. Think of it like we're just lining up all our Lego bricks, getting them ready to go. Next up, we create a series. And this is where the action really begins. We start adding up the numbers from our sequence, one after another. What we call the nth partial sum, or Sn, is really just the total you get after adding up the first n bricks from our line. So here's the absolute key. We say a series converges if, as you keep adding more and more terms, your running total gets closer and closer to one single specific number. It doesn't fly past it, it doesn't just wander off, it settles down on a final value. If it doesn't do that, we say it diverges, and basically our whole building project has failed. You can really think of it as a guarantee of perfect precision. It basically means that no matter how ridiculously close you want to get to the true final answer, I'm talking a millionth, a billionth, a trillionth of a unit away, you can always get there. You just have to add more terms to the sum. Your approximation just gets better and better and better forever.
Okay, so we get it. Our infinite sum has to converge. But how in the world do we find the exact right building blocks for a specific function like e to the z or sine of z? Well, that's where we bring in one of the most powerful tools in all of mathematics, the Taylor series.
Now, a Taylor series is a special type of series we call a power series. And you can think of a power series as our standard toolkit of building blocks. The pieces always have the same shape. You've got a constant, then a piece with z minus z0, then one with z minus z0 squared, and on and on. The only thing we have to figure out is the right coefficients, those a values, which basically tell us how big or small to make each block. But here's a really fascinating catch. A power series is unbelievably precise, but only within a specific area. I like to call it the circle of trust, but the formal name is the radius of convergence. As long as you're inside this circle, your infinite sum is a perfect match for the function. But the second you step outside that circle, the series diverges and the whole thing just descends into total chaos. And this is the universal recipe for finding those coefficients. It's the Taylor series formula. Now, I know it might look a little intimidating, but let's break down what it's actually doing. All this formula does is use information about the function at one single point, z0. It looks at the function's value at that point, its slope, its curvature, and so on. That's what all these derivatives are for. And it uses just that tiny bit of local information to build the entire function, piece by piece. It's like the ultimate blueprint for our project. So the whole process really just boils down to these 4 steps. First, you pick a point to be the center of your series. Second, you figure out exactly how the function is behaving right at that spot by taking its derivatives.
Third, you plug those derivative values into the formula to get your coefficients and actually build the series. And finally, step 4, you figure out your circle of trust. You find out exactly where your new series is a perfect copy of the original function. So the Taylor series seems pretty amazing, right? A perfect tool. But what happens when the functions we're dealing with aren't so perfect? What happens when a function has a glitch, a point where it just completely breaks down?
Well, that glitch has a name. It's called a singularity. The best way to think about it is like a hole in the very fabric of the function. It's a point where all the normal rules just break. The classic example is dividing by 0, right? At that exact point, the function isn't just a big number, it's undefined. It just doesn't exist there.
And that's the problem. Remember, our whole Taylor series recipe relies on being able to calculate derivatives at our chosen center point. But how can you possibly figure out the slope or curvature of a function at a point where it doesn't even exist? The answer is, you can't. At a singularity, our super powerful Taylor series tool becomes completely useless.
But don't worry. As usual, mathematics has a clever solution. When a function starts to misbehave, we just need to pull out a more powerful tool. And that's when the hero of our story makes its grand entrance, the all-powerful Laurent series. So what's the big secret behind the Laurent series? It all comes down to the building blocks it uses. A Taylor series can only build outward from its center point, using positive powers. But the Laurent series has a superpower. It can also build inward, toward the glitch, using negative powers. These negative power terms, things like 1 over z minus z0, are the special tools that are perfect for describing exactly how the function behaves right next to that broken spot.
And this is what it looks like. On the right-hand side, you've got what's called the analytic part. And yeah, that looks pretty much just like a Taylor series. But on the left, that's the principal part. That's where you find all those special terms with the negative powers. And that part is what perfectly captures the wild, chaotic behavior of the function as it gets closer and closer to the singularity. So what this means is that instead of a circle of trust, the Laurent series works inside a ring of trust, a shape we call an annulus. It's so clever. It just carves out a little hole right around the singularity in the middle, creating the safe ring where the series is a perfect match for the function. It lets us get right up close to the broken point to see what's happening without ever actually having to touch it.
Let's look at a quick example. Take the function cos of z over z cubed. It has a massive singularity right at z equals 0. You can't even dream of using a Taylor series there. But the Laurent series, it handles it no problem. See those terms like 1 over z cubed and 1 over 2 factorial z? Those are our negative power terms, the principal part, and they perfectly describe how the function just blows up at the origin. And check out the valid region. It works for any z that's not 0. It describes the function perfectly everywhere else except for that one single broken point.
And that brings us to one last thought. This whole journey, from simple sums to these incredibly complex functions, it reveals something pretty profound. It shows us that even the most complicated behaviors can often be broken down and understood as just the sum of infinite, simple, predictable parts. And that's not just some neat math trick. It's a really deep insight into how complexity itself works. So here's the question to leave you with. If any function can be described as just a series of simple numbers, what does that tell us about the fundamental building blocks of our reality?